Somehow.
Yeah, did
Somehow.
you sacrifice to the gods over the weekend so that you
Yeah.
could touch
Did
the
any of
board?
you go see the school play last week?
What?
I think.
Oh,
that's-
She Kills Monsters.
She
She
Kills
Saves Monsters.
Yeah, I
That's
was
a really
thinking
good
about
play.
you gamer types because it's about D&D.
Yeah, it's an RPG one. It's
Yeah.
a sad RPG one
It
though.
was pretty fun. I forget if there's episodes. I forget if they have more shows this week or not. That was kind of fun. Okay, so we have one question left in chapter 12, section 3. And we are trying to find the area between these two curves. Let's take this stuff off and start from scratch. So we're given these two polar curves, and at first glance it might not be obvious which is which, but let's think about it for a minute. We know that if we take the polar variable r and set it equal to a constant, the graph of r equals a constant is a circle. So we have two coordinates in polar, an r and a theta, and this equation only has an r in it, no theta, so that means theta can be anything, 0 to 2 pi, and it says that we are always root 2 over 2 away from the origin. So that's going to give us the circle. So that is this equation right here. So this is r equals root 2 over 2. All points root 2 over 2 from the origin. And that makes the other curve this one right here. Okay, and it says the region inside of this blob and outside of the circle. So that's how we are getting this little crescent region here. And of course, this crescent region goes all the way down. We want all that area. But as we've seen with area, usually it's ideal if we can do some sort of symmetry thing. So if we find this half crescent right there and double it, we are good. We have it all. We will have slayed this problem. Okay, so when you're dealing with polar, you're imagining a polar element. And a polar element is coming out from the origin, and then it whacks the first curve, and then it whacks the second curve. So the idea is that we're going to get the outer area, so this whole area here, and then we're going to subtract off this inner area. Okay, so we're going to do the outer area, which goes out to the blob, minus the inner area, which just goes out to the circle. So we will have the following as our setup. So we've got our generic integral for the area of a polar region. And we can factor the 1/2 all the way to the front. And let me give myself a little more space here because we're going to want to use some symmetry too. So let's put the symmetry in first. So that too is for symmetry. And then we have the 1/2 that's coming out, which is that 1/2. And then we have the outer radius squared minus the inner radius squared. RDRD theta. Looks like an extra D. So that's going to be our setup. And then our limits of integration, if we look at the graph, they appear to be 0 to pi over 3. All right, that's right. That looks like this intersection points at pi over 3. If it's not totally obvious by inspection, then we set the curves equal to each other and figure out where they intersect. So let's do that just to make sure we know how to do that. So if we want to look at the intersection, we're going to set root cosine equal to square root of 2 over 2. So this will tell us the theta values that they share. We'll square both sides. So cosine of theta will be 1/2. And then we think about a unit circle, whenever we have a basic trig equation, we want to go to the unit circle and just visualize where it is. You don't just randomly take the inverse, because an inverse trig function only has one answer, right? Inverse cosine of root 2 over 2, there's only one angle that satisfies that. because inverse cosine is on the top half of the unit circle. So that may be the answer, but you don't know. We want to think more generally. Cosine is 1/2. That's going to be putting us, here is where cosine is 1/2. There is where cosine is 1/2. There's where the Zamboni is. So this is on the 12 sector circle there, so we're thinking about the 12 sector circle. So we're at pi over 3. And then we have to sort of look at the context and decide, is that the one we want, pi over 3, or do we want this one down here, which is 5 pi over 3? It all depends on the problem.
We want both of them, but we're going to do 0 at the top.
So yeah, so we'll check. So when we look here, the pi over 3 matches what we see in quadrant 1, since that intersection is in quadrant 1. And if we were going to grab this intersection point down here, and we were going to sweep out that whole crescent, we wouldn't want to go from 5 pi over 3. We would want to go from negative pi over 3 to positive pi over 3. So we would choose this clockwise direction. We would, go down there to minus pi over 3 if we wanted to do the whole thing in one fell swoop. Okay, so pi over 3 matches what we see in the graph. So that all is good. So we've got our symmetry 2 and our coefficient of 1/2. Those wipe each other out. We're going to have the integral from 0 to pi divided by 3. The outer radius, that takes us out to the blob. So the outer radius is this blob one. And we square it. So that's cosine of theta. Minus the inner radius, that's the circle. We square that and we get 1/2. So there is our integral. That's going to represent the area of the whole crescent.
Why did, when you did the intersection, why did cosine pi over 2, square root of 2 over 2, or cosine theta, why did square root 2 over 2 turn into 1/2?
Because we squared both sides.
Oh. And also for the angle, we could have done 3 million 1 pi over 2.
Wait, what? I got lost. 3 million.
You could have done 3 million and 1 pi over 3.
Yeah, that if that makes the problem easier for you.
Go for it.
Go for it.
Yeah.
Multi-millions of pies,
I'm good.
right?
Yeah, I'm good.
We're going with this. We're going with the smallest pie.
The trick is you also usually want 0, because 0 is nice.
0 is always nice.
Which means that if you want your 0, you have to go to the next pi.
Then we have to go to this one, or we're gonna have some weird
You have problems.
phenomena happening.
No.
Okay, so, and this boils it down pretty nicely. This is a pretty easy integral to integrate. We integrate cosine, we integrate this constant, and we're going to go from 0 to pi over 3. Sine of pi over 3 is root 3 over 2. Minus, plugging pi over 3 in there is going to give a pi over 6. And then if we subtract 0, 0 is not going to contribute anything. Sine of 0 is 0. 0 times 1/2 is 0. So that's not going to contribute anything. So there is our answer. Could turn it into one fraction if you want, but it's not going to matter. Either way is fine. All right, any questions on how we do polar area there? The main thing is half theta r squared is our basic formula, but the theta is going to be used as a d theta since we're using a sliver of theta. So 1/2 r squared d theta is how we normally think of it. But if you were doing just a regular area of a sector, remember that the area of a sector is going to be 1/2 theta r squared. So we're using that basic formula, but we're going to creep it along with theta. So theta is going to be the d theta as it crawls through the whole sector. Declan, question?
I don't know if I want to ask you. How would we find the area of that middle section?
So the area, if we wanted the area of like this,
Yep.
so that's a terrible question.
Are you gonna ever ask us that?
Because there's not a distinct outer curve, right? That's going to be,
Would it
well,
be easiest
actually,
to just find what we just did and then find the area of that entire square root of
and
cosine
subtract it off. That's probably gonna be the
I was
fastest
just wondering if there
way.
was a shorter way to get that, or if we
Well,
could just do that.
Now that I think about it though, so if we were gonna do this inner region here, we would wanna parse it first right there. And this part here is just a part of a circle, so that we could do pretty easily.
Yeah.
Go to,
It's
And then
just
that other one's just
a signal.
pi 3.
yeah, and this other one is just the other one really, there is an outer curve that is unique. For a moment I was thinking that it was one of those curves where it touches itself, but it doesn't. When we think about a polar element emanating from the origin here, it's just gonna hit that one curve.
Yeah.
So we would literally just have to integrate this curve from pi over 3 to pi over 2, and that would give us that area.
And then we would just
And then
normal
add on.
1/2 pi r squared to find the other portion.
Yeah.
Well, what
Exactly.
about the left-hand side?
If you wanted this in here,
Yeah,
if you wanted that piece in there, that you would
or the entire left side? Like including the circle, semicircle?
so all this stuff,
Yeah,
It's gonna be the same problem.
then
just
it's
add a
gonna be similar to what we just did. If we found this area here and this area here, we could and double it, then we would subtract it off from the area of the full circle. If we do it that way.
There are a lot of ways to do it.
There's a lot of ways.
One thought is it's similar to like the vertical line test because there can only be one value of r for each theta with an r equals theta equation, right?
So when we draw that polar element, that theta value needs to correspond to both, because you're right. If you have weird frequencies,
Yeah.
if you have different
Oh,
periods,
true.
you could have some strange things happen.
So if it's
Right. So we
Got a
want that
normal
theta
period.
value to correspond to both those
yeah,
at the same moment.
yeah.
So we have to
Don't
just be a
ever-
little careful. No one's gonna ask you something super crazy.
So as long as it doesn't have a period besides pi or 2 pi, it'll always be
That radial line that we're thinking of right there, it's always gonna match the theta values for each.
gotcha. Okay,
Yeah.
makes sense.
Yeah. So if we had some, doubling of this angle in here, so that to plot that point, maybe for the circle it's pi over 6, but for that thing it's pi over 3, that would be a problem.
You could also just do it as two different integrals though, right? Do one of them at
Yes,
pi over 6 and
Yes,
one of them
that's
at
what you would
pi over
have to do.
Subtract them, yeah.
that's what you'd have to do.
Makes sense.
Break it into two problems and subtract them. Yeah.
You will make us do that, partner?
Nope. Nope. Too complicated. There's many other things for us to deal with. Many other things. Okay, so that is the end of the new content. So the final, when we look at the final, the final's gonna have 16 questions, 4 from each chunk of the class. 4 from exam 1, 4 from exam 2, 4 from exam 3, and 4 from chapter 12. So the chapter 12 stuff, we have 3 sections. 4 questions are gonna come from these topics right there. And if we go to the next slide here, this is a very generous outline of the exam. 16 questions, 16 concepts,
Seeing a pattern here.
one-to-one correspondence.
Don't
So-
study any of those.
So these are where we want to focus on for studying for the final. And so here are the topics for the new stuff. So we want to be able to convert a parametric curve to Cartesian. We want to be able to graph it, convert polar to Cartesian, find slope of tangent lines, and find area between curves. So those are the 4 topics for chapter 12.
Can I get a note card for this?
Yes, you get a note card. You get,
What?
That's where I'm just gonna write down, reminder, do not forget.
so, yeah, so, oh, I didn't even write it on there, did I? Yeah, you get a note card, both sides of a 3x5 note card for the final.
Oh,
Can you
cool.
just print one out? I did.
Yes.
You know what I'm talking about?
Yeah, so if you look under handouts, do I have it there? Yeah, you can do that. You can do what you just said. I thought I had a sample note card up here that you could just print out so that you were doing it on paper instead of on a note card. I'll add it in here under handouts. It's simple enough. Yeah, so 3x5 note card though for the final.
Bust out the monarch.
I can't believe I didn't write it in there.
I don't know.
Set to go. Just zoom in. I'm just gonna sit next to you in the exam and just steal your glass and be like,
I
alright,
know
good.
it's quite blurry
Every single
today.
handout on one page.
Yeah.
Yeah, print it all.
3 inches.
Very blurry.
Yeah, that's what the glasses are for.
Yeah, that's, you didn't say a magnifying glass is excluded, which means we're allowed to bring it.
Also, there's the z-axis.
Yeah, but the
Yeah.
problem is, imagine you're taking the test and you just see
Imagine,
other
I
people
just
just
going,
going, oh shit, my note card's on fire.
Can we 3D print?
You can write on the edges, you mean?
I'm saying I could go 3 inches in the X, Y,
He
and.
never,
Yes,
like,
it's a 3x5 note card, you did,
Yeah.
Area
You did not
and
limit.
volume must match.
I'm sorry here, friend, but just like graphing, you did not limit our Z coordinate.
Yeah.
Right.
As such, we get maximum Z coordinate.
Yeah, so I need to make this a 3 by 5 by.
Point
But
one.
we gotta change the rules, it's already in the,
Yeah, you've already written it down.
you already.
What are you cheating?
To be late?
You
forgot the note card in the first place.
yeah, no,
Thank you.
yeah, no, if we keep doing this, you might just go, no, no
Yeah.
card.
Hey,
What
to
note card?
Yeah.
It wasn't in the rules.
I'm gonna bring a little incinerator. Toss all the note
Shredder.
cards.
I know, you should have it like this
Just like
long.
our grades.
Like,
Yeah,
throw them in
this
the
thick.
Yeah, if you want to make your note card 1 inch by 15 inches.
Yeah, I'm just gonna bring in a basalt monument with like the equations.
I know,
carved
if,
in.
if I.
Maybe we should do math because we have a final exam in 2 days.
No, this is much more enjoyable.
If my paper is same area or less, can I use it?
Yes. It's all about area. 15 square inches times 2, 30 square inches.
30 square inches, that's the space you're working.
30 square inches.
I can have a 16 inch.
Okay, so where do we want to start?
Yeah, like hyperbolic.
When we look back here, volume using shells or washers, should we do an example of that?
Probably.
No.
Just one that we
Test 3.
Is it or? So will you tell us to use one or the other, or?
Yeah, I'll tell you which one to use. Yeah, I'll tell you. I'll tell
So we
you.
do need a notebook.
Because
Yeah, absolutely.
Choose one of them. Okay.
I did
Do
it.
we have time just to do 10 problems?
16 minutes, 16, what?
Do we have time just to do those first problems that doesn't include chapter 12?
If we start doing math, I think.
Let's bust in, partner.
So should we do a shell or a washer first, or? Okay, so let's suppose that we have something that looks like this. We'll call that y equals the square root of x. We'll call this x equals 4. So we've got those two curves, and let's rotate this around the y-axis. Actually, let's be a little more general. Let's rotate around x equals -1. Just to make sure that we've got all these little details. So the first thing, when we're rotating around an axis, we have to keep in mind that parallel element or parallel representative rectangle, however you think of it, has to be the setup. It's got to be parallel. So you want to draw, you can always draw your integration element vertically or horizontally. If you want to do shells, it has to be parallel. So parallel shell, parallel shell. And then we know that the area of a shell, which is nothing more than a cylinder, is 2 pi times r times h. Circumference, 2 pi r times h. That's going to give us the area of the shell. So 2 pi r h. Now we have to figure out, well, where is the r and where is the h? And when we look at this picture, that distance right there is representing the radius of the shell, and the height of this green element here, that is representing the height of the cylinder. Okay. Now, before we replace the r and the r and the h, let's think about whether we're integrating with respect to x or with respect to y. Is it going to be a dx or a dy? So if we think about if you think about this element as a rectangle, its height is h and its width or its thickness is dx. That is what indicates whether we're integrating with respect to x or y. So if you have a vertical integration element, it's always dx. You're integrating with respect to x. That means the r and the h need to be replaced with expressions in x. Okay, so let's go with the r first. What is the radius as a function of x?
X plus 1.
So if we look right here, this distance, that's r. This distance right here is 1. This distance right here is x, so that's going to be x plus 1. Or you can think in your mind, it's always, if you're doing horizontal, it's always the right x minus the left x. The right x is called x. The left x is -1, so it's x minus minus 1, which is x plus 1. So you can think of it geometrically, or you can think of it analytically, right minus left. Both are going to work totally fine. So we have an x plus 1 for the radius. And then how about the height?
4 minus y squared divided by y squared.
So if we're doing a vertical distance, this is vertical, it's going to be the upper y minus the lower y. The upper y is square root of x. The lower y is 0. Right? The upper curve is y equals square root of x. The lower one is y equals 0, so it's root x minus 0, so just root x. That'll be the height. So now we have the area of the shell at a random x. And if we want to just do a quick check in our mind, we know that the x values are starting here at 0 and they're going all the way across to x equals 4. If we plug in x equals 0, we should get a cylinder with area 0. If we rotate that around, we're just taking a point and rotating it around, there should be no area. So if we check, we plug in 0 here, yeah, square root of 0 is 0, 0 times anything is 0. And then if we check the outer cylinder is going to have a height of 4 and a radius of 2. Everyone agree? I said that wrong. This is 4. The height is going to be 2, and the radius is going to be 4. So that distance there is 4. This distance here is 2. So that cylinder is 2 pi RH, and that will match here. We'll get the right area. So if we plug in a 4 for the x value there, we're going to get 4 plus 1 is 5. Square root of 4 is 2. Multiply it all out. It'll match. And what is the radius of the cylinder there? I also just realized we have an axis. We're rotating around the blue line. What is the radius? 5. 5, not 4. The radius is 5. So if we plug in the x value of 4, we get the radius of 5. 4 plus 1. Okay, so then the integration to get our volume, we're going to integrate from literally where we see these green vertical lines, 0 to 4. Not -1 to 4, 0 to 4. Everybody follow that? And then let's turn this square root into fractional exponents because we love fractions. So it's easier to integrate with fractional exponents, of course. So then we just do the math here. This part shouldn't be too hard, hopefully. So add 1 to the exponent, divide by the new exponent. So dividing by 5/2 means multiplying by 2/5. Add 1 to this exponent, get 3/2. Divide by 3/2 means multiply by 2/3, 0 to 4. Plug in the 0, plug in the 4. Thank you. They're just singing. They're like getting louder. They're louder than a Zamboni.
Giggle, giggle.
And the frequency is like irregular.
Zamboni
is very steady.
Monotonous, same thing.
All right, so any question on the concept of the R, the H, how we figure out if it's dx or dy?
Same question, but if we were rotating around the x, we'd have to find a y value.
So if we did the same exact one and we're rotating around x, so if we do this type of thing, that again is 4, this again is square root of x. If we rotate around this axis, what method would we naturally be using? Disk, washer, shell. Yeah, that's going to be a disk. If we draw our vertical element right there, unless you want to do it as a washer or a shell.
Either way,
This is easy, doing it as a disk. It's just pi r
we
squared.
did it as a shell.
So let's do it as a shell. So if we do it as a shell, that is going to be the random horizontal element at y, sleeping rectangle, and that's going to rotate all the way around. That's going to create a radius right here. There's the radius. The height of the cylinder is now sideways. So the area of the shell, again, 2 pi rh. So 2 pi. The radius is now vertical. So it's upper y value minus lower y value. This upper y value is y. The lower y value right there is 0. So it's y minus 0 for the r. And then the h,
Left minus right, or right minus left.
right minus left. Any horizontal distance is right x value minus left x value. The right x value right here, that's x equals 4. The left x value is
Y squared.
y squared. X equals y squared. So if we take that x value on the right minus that x value, it's 4 minus y squared. Would be the height. And then how about the limits of integration?
0 to 2.
0 to 2, exactly.
Plug in 4. Get the y value.
Exactly. If we plug in the 4 right there, square root of 4 is 2, so that tells us that we can imagine there being horizontal elements all the way from 0 all the way up to y equals 2. Yep. So we'll go 0 to 2. And then we would multiply this out. And then integrate.
And then integrate.
Yeah, integrate part.
So the one above that, when you go from 0 to 4, that's because we're going vertically.
We're using vertical elements, so we're imagining all these vertical elements from x equals 0 to x equals 4. So we're integrating with respect to x, and that means that all those x values, you can imagine a cylinder. So you can imagine one of these vertical green lines at all the x's between 0 and 4. And we should be visualizing like this concentric cylinder thing. You know, where we're finding the area of each cylinder progressively from 0 all the way out to 4, and then adding them all up. Should we do a washer?
Yes.
So let's do a washer with, let's suppose we have something like e to the x. Please be able to graph e to the x without thinking.
What's E?
E, the letter before F. So
Grade.
the only letter that we don't use for grade. Why did we skip E?
Because it's too fractional.
So let's suppose that we have that, and let's suppose that we are going to find, let's draw a vertical line right here. We'll make that at 3. And let's suppose that we are going to take this region in here, and let's rotate it around the y-axis. Okay, so if we're going to use a washer, should we use a horizontal element or a vertical element if we're going to use a washer? Horizontal. So if our axis is vertical, parallel is going to create a cylinder, perpendicular is going to create a disc or a washer depending on whether there's a gap or no gap. So here, if we draw this horizontal element right there, that's the random element at y. And if we're going to go around the y-axis, that's what we need. So this distance from here to here is going to be the inner radius, and the distance from there to there is going to be the outer radius. So you're imagining that little blue segment rotating around, and it's going to create a washer. So if we take the blue element and rotate it around, you know, we're ending up with that situation. And so the inner radius is this distance, outer radius is that distance. And to find the area, we're doing pi r squared minus pi r squared. Pi r outer squared minus pi r inner squared. So the area of our washer is pi times r outer squared minus r inner squared. Okay. Now, before we substitute in here, are we integrating with respect to x or are we integrating with respect to y?
Why?
We're going to integrate with respect to y because we've got a horizontal element there. And that horizontal element is indicating a rectangle that's on its side that has thickness dy. Right? So that's going to be the indicator that the r sub 0 and the r sub I have to be rewritten with y's. Okay? So now, when we look at this, the inner radius, so we said that this was y equals e to the x. That's a horizontal segment, though. Horizontals are always differences in x's. So this curve right here is presented as a y value. We want to change it to an x value. So it's going to be x equals natural log of y. So this distance right here, this r inner, the x value right there is natural log of y. What's the x value right there?
1.
Huh?
You're on the wrong one. So you're going from x equals.
If we're doing the inner, it's natural log of y minus 0.
Yeah, never mind.
So natural log of y minus 0. So that's the inner. So how about the outer one? So the outer, that whole distance is 3, no matter what. Doesn't matter where you draw your horizontal element, it's always 3 units away from the y-axis. Okay, so now we can plug stuff in. So the outer radius is always 3. The inner radius is what we just found it to be. So the inner radius is that one. Quantity squared. So that is the area of the washer at a height of y. And if we want to find the volume will be the integral from, well, if we're just doing this in here, we're not going all the way down to the origin. Oh.
1 to.
So if we're just finding that area, rotate it around. So that volume is from 1 to,
Natural log of 3.
so this intersection point up here is, what is that y value?
E cubed.
E cubed. This would be 3 comma e cubed. So we're going on the y-axis, not the x-axis. So the y-axis for this curve, the y values are going to be from that part. So y equals e to the 3. So we would go from 1 up to e to the 3. So this y value here is 1. So that's 3 comma 1. So we're going to go from 1 to e cubed. 1 to e cubed. And then that whole quantity there, so pi multiplied by 9 minus, they like to write natural log squared like that in this book. So we'd have that. Now, do we know how to integrate natural log squared? That is not a polynomial, so you can't add 1 and divide by the new exponent. If we had any hope of integrating this, what technique would we probably try?
Trig sub.
We could try trig sub because we have a difference of squares. Could try trig sub. If we were just to try to integrate this on its own, the way we integrated natural log was with integration by parts. So it might be, I don't even know off the top of my head because this is not a problem that we would ever see. But when you're just making up things, you're going to get functions that aren't nice. So, yeah, I would not put something on there that we haven't integrated several times in this class, so. Yeah, it'd be interesting to try to figure that out, though. Okay, so we've done a washer and we've done a shell. What's next on our list? Arc length surface area?
Okay, we need an integral solver for that, Desmos.
Yeah, you could use Desmos, yeah. So arc length or surface area?
Arc length.
Arc length? So if we look at an arc length problem, so the idea is that we want to figure out, you know, the length of a curve. And the general idea is that arc length, which is usually represented with a little s, is going to be the integral. If you were so lucky, if you had a curve that had a little tape measure bent on it, it would be super simple. This integral would just be the double star minus the single star. But we don't have, these are s values. We don't have the s values, right? So we can't do that. We have to convert the s values by looking at switching over to dx or dy. And if we switch to dx, this is 1 plus y prime squared inside there. And then these are now x values, say x0 and x1. Okay, so that's why we have to convert over to x's, because we have information about x. We don't have information about the movement along the curve. We don't have anyone measuring in that way in our coordinate system, right? We don't have this. Okay, so let's suppose that we have some function. So let's suppose we have y equals, let's just do the square root function since we have been doing that already. So let's suppose we have y equals square root of x, and let's go from 0 on the x-axis to 9. So we want to know, how far is that? Along the curve. So along the curve, we're going to integrate from x equals 0 to x equals 9, the square root of 1 plus the derivative squared. So we have to come over here and find this derivative. So that's going to be 1/2 x to the negative 1/2. And then we square it. So if we square it, we end up with, 4, if we square that, we're going to get an x in the denominator. Everyone agree with that? Right, it's 1 over 2 root x. And if we square that, so 1 over 2 root x. If we square that, we'll get a 4 and an x in the denominator. So that's what's going to go in here. So we have 1. So we've got that. Now again, just making up problems out of thin air, the chances of ending up with something integrable, it's like throwing darts and trying to hit a bullseye. Not easy.
Yeah.
So do we know how to integrate that? One thing you might do is say, okay, well, let's first try a couple of things. This would be the first thing I would try is get a common denominator. Does that look any better? You know, the problem here, let's make sure you understand the problem, is that u substitution would be the natural choice. Can we let u equal this? And if we let u equal that, that's going to give us something crazy. If we let u equal 1 over 4x, and then we take the derivative of both sides, so this side we would write as x to the minus 1 divided by 4. So then we're going to get du equals negative x to the negative 2 divided by 4 times dx. So this is going to be so that's what our problem is. So we don't have this to absorb that. So obviously on the test, I've got to give you something where you can use U substitution or you can integrate it immediately. Arc length is the worst. Trying to create a problem with arc length that you can integrate. Do you remember the one that we did a couple of times? There had to be a very special type of curve that we used a difference of squares and then a sum of squares. Do you remember that? This is, so if we have, let's go to arc length for a second here.
A circle curve is the easiest.
Where was
Curve,
arc?
You saw it, 6.5.
Where, it's 6.5?
Like-
Oh, thank you, right there. So remember these guys. We had a sum of squares. Let's see, that one was easy. Where is the, here. So we had to have this really concocted curve. And when we found the derivative and squared it, we ended up with a -1/2. So then when we added the 1, the only change was to the middle term, which turned our difference of squares into a sum of squares. Remember that? Question?
Is it possible to where we could solve it with just geometry but not the integration?
Only if the curve is like like you said, a circle.
Since the curve is a circle, we wouldn't be able to use integration, but we'd be able to use the,
Geometry.
Yeah.
Yeah. But like that curve there, we don't know the.
Or if it's a linear curve, you can do it with either, because you end up with just an x underneath, right?
Yeah, if it's a if you end up with if you end up with x in the numerator underneath, then it will work out
And then
fine.
it works fine.
Then it'll be fine. So take a look at this one. Make sure you can do this one. Remind yourself how to do it with this difference of squares, because that's a pretty common one. All right, so surface area. Let's pick a random surface area one. Trying to create one from scratch is kind of hard, so let's just grab that one and we'll redo it. There's no way we remember it.
Bless you.
Thank you.
It'll be okay.
Okay, so here's the surface area problem. So we've got this curve. We don't know what it looks like, but it's a square root. If it's a curve that it's important to know the graph of it, I will give the graph to you. I would never expect you to be able to graph that. But what you should be able to think in your mind is that this is a bird wing type of thing, right? All square roots are these things in quadrant 1 that look like a bird wing. And we're going from 1 to 4, and we're going to rotate around the x-axis. So in your mind, all we need to know is that we're only going from 1 to 4, and there's some sort of curve like that. Something like that.
Isn't this part of a circle?
Yeah, it is part of a circle. Yeah, we don't know what the center is unless we do a little math, but yeah. Okay, so if we rotate that around the x-axis, same idea that we just talked about. So we definitely need the derivative of this curve. So we're going to do 1/2 times 5x minus x squared to the -1/2 multiplied by the derivative of the base. So we'd have that. There is the derivative. And then we square it. That's y prime. So then y prime squared, let's see, that's going to put in the denominator, we're going to have a 4, and the 5x minus x squared, that's to the -1/2, that pushes the square root into the bottom, but then we square it, so the square root goes away. And then in the numerator, we'll have 5 minus 2x quantity squared. So there is derivative squared. And our generic formula for arc length, surface area. So surface area, I think they use a capital S in this book, capital S. So surface area is 2 pi RDS. There's our generic formula. And then, again, we don't have S values. If we did, then it'd be easy. We don't have S values. So we have to convert. So if you're trying to think conceptually about that formula, 2 pi r is the circumference of a circle, and then ds is a little slant height. It's like the slant of a frustum of a cone. All right, and that's kind of what you're imagining here. When you rotate this around the axis, you're imagining that as a little cone frustum, the bottom chunk of a cone, with a little slanted corner to it, slanted edge. Okay, so for us, we have 2 pi r, where r is this distance right there. All right, it's like a disk. That r is just given by the y value, the function. So the function is square root of 5x minus x squared. There's our function, that's r. And then ds, same thing that we did in the last problem, square root of 1 plus y prime squared. So square root of 1 plus y prime squared, which we already found. There. And then we'll combine those two square roots, and our limits of integration are 1 to 4. So if we take two square roots and we multiply them together, we multiply the insides together, so this here gets multiplied by the 1, and it gets multiplied by this whole fraction. All right, so it's the square root of the two insides multiplied together. So we have a big, huge square root, and 5x minus x squared times 1,
5x minus x squared.
plus, and then over here it wipes that part out, right? That whole denominator goes away. This part of the denominator goes away. The 4 is still there. So we end up with, let's see, let's FOIL the numerator out. So we get 25 minus 20x plus 4x squared. And the denominator, the only thing that's left is the 4. Any questions up to that moment? We'll distribute the 4 into the numerator. And that's going to leave us with, hopefully, some simplification. That's supposed to be a 1 at the bottom. So we're going to have square root of nasty, hoping to get better. So 25 divided by 4. And then 4 into this one gives minus 5x. That's cool. And then 4 into that one gives plus x squared. So we have a whole bunch of cancellation. We end up with 2 pi integral 1 to 4. The only thing that's left is the 25 fourths.
Yep.
Square root of that is 5 halves.
Yep.
The 5 halves comes to the front and gives us 5 pi integral 1 to 4. What does that become?
3.
3. 4 minus 1. 3. The integral of a differential is the upper minus the lower. So this will be 15 times pi. That'll be our arc length. All right, surface area. Surface area.
Can you go back up real quick?
Yeah.
So when you're combining the square root functions,
Yep.
when you're foiling it out, so when you're moving it over, so I see the part where,
This numerator?
yeah. So it's canceling out with the bottom, right?
Yes. Yep.
And then how are you foiling it out? Where are you getting that?
First outer inner last.
Okay.
So
But when you times it by that other,
Well, it cancels with the
Oh,
denominator.
it cancels with, okay, and then you're just foiling it out, okay, perfect.
So yeah, so the numerator, first, outer, inner, last. The denominator, the only thing that's left is a 4. So this piece here only wipes out
The
that.
denominator, yeah,
So it's just going to cancel with that denominator part.
we're good.
So this is why it's going to be important, like on these tests, that I've got to create functions that end up being integrable after all this shenanigans. A little bit of a headache. Okay, so emptying of a tank. So let's pick let's pick something in the middle. Let's pick the cone. This one is sort of not the hardest and not the easiest. It's the one in the middle. So we've got this conical tank. We've got a radius up here. Let's suppose that radius is 4. And let's suppose the height of the tank is 10. And we're going to assume it's filled with water. And we're just going to drain it right out, right there. Or we could do it at the top. Actually, let's do it at the top. This book primarily does them right out the top. So we'll drain it out the top. We're going to have a pump that's doing the work then instead of gravity. Okay, so if we're going to drain it out the top, what we imagine then is a cross section. So a cross section is 2-dimensional, cross section, and then a slice is 3-dimensional. So we start with a cross section, which is just a disk, and then when we turn it into a slice, we're adding thickness. We're adding dy. So that turns the cross section into a slab, turns it into a slice. All right, so there's our radius right there, our generic radius for our generic cross section at y. So we need to know the area of that disk as a function of y. Right, we're going to integrate with respect to y because horizontal element, right? All these cross sections of y have to travel the same distance. If you take a cross section of y, all those particles of water have to travel the same distance, so we focus horizontally. Okay, so to find the area of this disk, what are we going to do? Say that again?
Rise over run.
So we're going to think about squashing it into 2 dimensions and using rise over run. So if we think about this as a coordinate system here, we're going to mash this down into just 2 dimensions. We know that this point right here has coordinates 4, 10. We know this point here has coordinates 0, 0. So we know that the equation of this line is y equals mx plus b. Well, the b is 0 because it goes through the origin. So it's just y equals mx. Slope is rise over run. So it's rise is 10, the run is 4 times x. And if we simplify that, we get 2/5 x. So that's the equation of the right edge of the cone. But we are looking for a horizontal distance right there. We know that the area of the disk generically is pi times the radius squared. But we need to find a horizontal distance here. So what we're going to do is solve for x. So we're going to have 2/5 y equals x. And that's what comes in up here. 2/5 y is the radius. And now we have the area of the disk at a height of y.
It'd be like 2/5 y minus 0, right, which is that.
It's 2/5, yes, exactly. So the y-intercept, so when we look at the equation of a line, mx plus b, if we're going through the origin, b is 0.
Yeah.
So we get y equals mx, but then we want to isolate the x because we're measuring the radius as a horizontal distance, and that's what x measures. X measures horizontally, y measures vertically, and so now we have 4/25 pi y squared. So that's the area of the disk. All right, so that's the cross section. And then if we tag on a dy, now we've added thickness to it. We've got a slice of water, a little slab of water, and now we can find the volume, not the volume, but the, what's it called? Work. Work done in pumping, work done by the pump. So our generic formula for work is the integral of ADD volume. So work is ADD volume, and force is ADD area. So the force is when we're putting pressure onto a wall or onto a face. So work, ADD volume, acceleration due to gravity, 9.8, density of water, 1,000. So those are going to be given to you. And then the second D, you can think of it as depth or distance. If we're thinking about this slice of water moving, you can think of it as distance. On the force against the wall, you definitely want to think of it more as depth, but it doesn't matter. Either one fits. So we're looking for this distance right here.
10 minus y.
So the upper, it's a vertical distance. Upper y value is 10. Lower y value is y. Right? So 10 minus y. So that's the ADD. Now volume is not the volume of the cone. It's the volume of that little slice, that slab of water. And the volume of a slab of water or a slice of water is its area multiplied by its thickness. So there's the area multiplied by its thickness. So that right there is the volume of a slice of water. And then our limits of integration, we have all these cross sections of water from 0 to 10. And then we integrate that. So we pull out the constants. Let's write one more step down. So we're going to pull out the constants. So we pull out 9,800, pull out the 4, pull out the pi, divide by the 25. And the only stuff that's left inside this integral are 10 times y squared and minus y times y squared. So that's all that's left. And then integrate that with the power rule. So all of these are getting pulled out. Pulled out, pulled out, pulled out, pulled out, pulled out. The only stuff that's left, 10 minus y and y squared. So then the slight modifications of this, if the drain was, say, 2 meters above the top of the tank,
12 minus.
then what would change? The distance the water travels. Instead of it just traveling up to a height of 10 and being pumped out, it has to travel to a height of 12, so its distance would be 12 minus y. And that's the only thing that would change. There's still only slices of water from 0 to 10, so the limits of integration don't change.
The limits of integration will only change if the water was only filled up, like the question said, only filled up to 8 meters high in a 10-meter tall cone.
Exactly. So that's when the limits of integration always physically reflect where the water is.
On your limits of integration, the drains at the top, would it not be negative 10 to 0?
It depends on how you draw your graph.
Okay.
So you can put your coordinate system wherever you want,
And then it would change everything.
and then it would change your limits of integration, it would change the distance like the setup for the distance traveled.
But it would be correct if you did everything right.
Yeah, absolutely.
Can we put our like coordinates where the cone's on top of Mount Everest and 0, 0 times sea level?
You'd have to change
Zone
gravity.
exam.
Would you want to?
Yeah, you would
Yeah,
have
write a
to
custom
account for the change
exam,
in
give
gravity
all
there.
those to you.
Yeah, we'll give Zach a custom exam.
Yeah.
that involves Mount Everest, and involves,
But
3 million
Yeah,
pi.
the rest of us get the
Allowed
easy
to.
one.
Don't.
Okay, you asked for it. He's asking for it. Okay, so that is work.
Oh, you need joules too at the end, don't you?
Yes, exactly. Yeah. So when all is said and done, yeah, we're going to end up with joules.
Big number joules.
Yeah, a big number of joules, a ton of joules.
So many joules.
We'll be loaded. Okay, so work empty in a tank. Hyperbolic derivatives and integrals.
Let's skip that, because
It's really should be easy if you do enough practice with it, because there's nothing tricky about it. You just have to know your.
Oh, right, yeah.
We definitely want to do some trig sub.
please.
Definitely want to do trig sub. What about powers of products? That's also very mechanical. These two are super mechanical. Should we do powers, or should we go to more conceptual trig sub and improper integration?
So we can skip and come back.
Yeah, if we have time.
Yeah, let's do trig sub for sure, because that's always a bugger.
Yeah.
Okay, so trig sub. The main thing you're looking for with trig sub is a difference or sum of squares. That's sort of the classic, oh yeah, trig sub might work. So let's try to concoct something here. So if we have something like, this, this we could do with u substitution. So maybe I'll modify. That's okay though. We could do this with u sub. Let's do it with trig sub. Doesn't matter. That's the basic setup for trig sub, is that we have a difference of squares somewhere, or a sum of squares somewhere. Okay. So we ideally are going to set this up so that we have a sum or difference of squares with a 1. Sum or difference of squares with a constant value of 1 there. So we're going to factor out the 9. Let's see. So that 9 comes out in the denominator as what?
9 to the 3 halves.
9 to the 3 halves. So let's just write it generically initially like that, right? Whatever that power is, if it's a square root, comes with it. If this was to a power of 4, it would come out with a 9 to the 4th. Whatever that exponent is right there, that has to, if you pull something out of there, it's got to come with that power. Okay, so then we get a 1 minus. And remember, there was no 9 over here, so we imagine multiplying by 1, and then this is the 9 that we factored out. There's still this division by 9, and so we're going to write this as x divided by 3 quantity squared. Now we've got it written in a very nice trig sub form. Now we can say that x over 3 is equal to sine, secant, or tangent. Sine. So those are the only 3 choices, sine, secant, or tangent. And you're picking the one that simplifies. 1 minus sine squared simplifies. So that's why we pick sine. 1 minus secant squared is not going to simplify. 1 minus tangent squared is not going to simplify. So we pick the one that will work. So x over 3 is going to be sine of theta. We take the derivative of the equation here. Write it like that. Write it as a differential equation. And then we come back up and substitute everything in. So this was 1 over, do the denominator first, square root of 9 is 3, 3 cubed is 27. And then in the numerator we have an x. So here, if we isolate the x, we get x equals 3 sine theta. If we isolate the dx, we get dx equals 3 cosine theta times d theta. we've got that. And in the bottom, we have 1 minus sine squared of theta raised to the 3/2 power. And that was the whole point, because 1 minus sine squared is cosine squared. It collapses it into one term. That is the whole point. So this is going to be 1 over, let's see, we can do some simplification here, right? This is going to be 9, so it's going to be 1/3. And then we have sine times cosine up top. And then down below, 1 minus sine squared is cosine squared, raised to the 3/2. So we're going to end up with cosine cubed of theta.
Which will cancel one with cosine.
One of the cosines cancels. Yay. So we've got that. And what technique do we use here?
U sub.
U sub.
Or actually, we could use the, what is it, powers of sine.
Yeah, this is essentially powers of sines and cosines.
Yeah. Cosine to the -2 sine.
And so if we let u equal
Cosine.
cosine, the derivative of cosine is sine right there in the numerator. There's a minus sign in there, but we'll get to it. So if we let u equal cosine, du is minus sine of theta d theta, and that's in the numerator. So that's perfect. Couldn't ask for a better u sub. So this will be 1/3 integral. Sine of theta d theta is minus du, so we'll put the minus out in front. Put the du right there. U is cosine, so this is going to be u to the -2. That is integrable. So we're going to have -1/3. We add 1 to the exponent, divide by the new exponent, plus c. This becomes positive 1/3 multiplied by u to the -1. So that's 1 over u, 1 over cosine, plus c. Or you could write it as secant, 1 over cosine is secant, doesn't matter. Okay, we're almost there. Our original was x, so we got to get back to x. So we build our magic triangle. Takes us between x's and thetas. So here is our magic triangle. There's theta. Sine of theta is opposite over hypotenuse. So we always use a right triangle as if it's positioned in quadrant 1. This will give us 2 of the sides. We find the third side using the Pythagorean theorem. It should look something like what's in the original. And now we can do our final step. So 1 over cosine. So cosine is adjacent over hypotenuse. 1 over cosine is hypotenuse over adjacent. So we're going to end up with 1/3 hypotenuse over adjacent plus c. And you can, of course, cancel the 3's. There will obviously be a trick. Oh, shoot, we should take a break.
Should we?
Where did that,
Nah, man.
where did that 3 come from 1 over cosine? It wouldn't just be 1 over square root of 9.
Say that again. Where am I looking?
That right there. yeah.
This one here?
The 3 that's in the answer,
Mm-hmm.
on top in the numerator.
That one?
Yeah.
So cosine, so we're looking at this triangle. Cosine, according to this triangle, is adjacent over hypotenuse. And then we flip it over, which is what putting the 3 in the top. Yeah, which is secant. Hypotenuse over adjacent. I pause that one. Okay, so improper integration. This is the first really abstract concept that we encountered, trying to find the area of an unbounded region. That's super non-intuitive at first. And when we're thinking about this, we're thinking about these functions that are approaching 0 really fast, and whether they approach fast enough that you have finite area. So we had 2 types of improper integrals. We have the ones where we are looking at this horizontal tail, and then ones where we're looking at this vertical tail. And we want to know, is the area finite, even though it's unbounded? And we talked about our initial instinct was probably wrong, that, if the area goes on forever, it must mean that it's infinite area. But it's not, often. So let's take a look at a couple of examples. So let's suppose we have... So we saw that our threshold function was 1 over x, that the power had to be bigger. So let's just do a quick confirmation. If we see something like this versus something like this, and if we go from 1 to infinity for both. So these are 2 classic types of problems. The very first step we should always take with any of these improper integrals is to use a limit. So right away, we know that this is the first step. Rewrite it with a limit as b goes to infinity. So first step. Notation is very important, so don't forget your limit. And both of these have the same sort of format with the first step. So integrate, turn to limit of integral. So up here you have an improper integral because you have the infinity. Down here you have the limit of a definite integral. So it's a definite integral as soon as you have 2 limits of integration. We look at this first one. Add 1 to the exponent and you get -1/2. Divide by -1/2. Same as multiplying by -2. 1 to b. Over here, we're going to do the same type of thing. Add 1 to the exponent, we get +1/2. Divide by +1/2 means multiply by 2. And right away, you can sort of see, like we know based on what we've done, that this is bigger than 1, so we're going to get convergence because that denominator is going to grow fast, which means the fractions are going to shrink to 0 fast. Here the power is only 1/2, it's less than 1. And down here is where we notice it. This is going to put an x in the bottom. This x is in the numerator. So as b goes to infinity, this is going to be an infinite value versus this one, which is going to be a 0 value. So here we have the limit. Let's factor out the -2. Limit of, so 1 over the square root of b minus 1 over the square root of 1. And as b goes to infinity, 1 over root b goes to 0. So this becomes -2 multiplied by -1, which is 2. So that tells us that the area beneath that curve is 2. So it's finite. Area is finite. Region is unbounded. Here, we get the limit, factor out the 2, we get the limit square root of b minus 1. And that limit as b goes to infinity is infinite. So even though that both of these curves have the same shape, It's just that that one goes down way faster than the other one. Fast enough that you get finite area. So with improper integration, the two things that students tend to lose points for are notation, so make sure you have limit, and then evaluating the limit wrong. So just make sure you evaluate your limits carefully, and if the denominator goes to infinity faster than the numerator, 0.
You're not gonna give us a graph, right? There's no need for that?
Yeah, there's no need for that with these ones. The one type of improper integral, so if we have something like 1 over x cubed dx, so the improper integral where we have a vertical tail, it's not as obvious. So if we look at this one, it's not as obvious that that's not a definite integral. When you look at that, based on most Calc 1 classes, you see numbers and you say, oh, it's a definite integral. But no, it's not a definite integral unless this function is defined on that interval. And the function is not defined at 0, so it's not a definite integral, it's an improper integral. So here, same idea, we have to introduce the limit. Whenever it's improper, we introduce the limit. And here we have to be a little more careful. It's not just as, b goes to infinity, like that's pretty simple. Here we have to be a little more thoughtful. So, and it doesn't matter what letter you choose, I'm going to just pick an A. And where is A going to go to? 0 from the right-hand side. All right, so we're imagining our interval, 0's over here, 1's over here, and we're getting closer to 0 from the right side. So very important that it's a one-sided limit, because the two-sided limit may not exist. When you don't put that little plus, you mean a two-sided limit. So we don't want a two-sided limit, we want a one-sided limit. And so we end up with that. And now in our minds, is this going to converge or diverge? Diverge, because the power is bigger. We know that this would converge horizontally, but it's switches, right? If this converges horizontally, it's not going to converge vertically. We don't have a function that converges in both places. It's one or the other. 1 over x diverges in both places, but we don't have a function that can get close to both axes fast. It's one or the other. And so we should expect divergence here. So that's an important thing to have in your mind, that you're trying to target divergence. So we've got that. We'll factor out the -1/2. It's usually a little easier to do limits if we factor out the constants. So this is going to be 1 over x squared with a 1 in it, and then subtract 1 over x squared with an a in it. And here is where it's very common to make a limit mistake. So frequently we're taking the limit at infinity. And you would say, oh, that goes to 0. But we're not taking the limit at infinity. We're taking the limit at 0, not the limit at infinity. So we have to be careful here. So when we think about this, the denominator is always positive for two reasons. We're plugging in positive numbers, and a is to an even power. So this denominator is getting closer to 0 through positive values, which means this part right here is going to positive infinity. All right, a is getting closer to 0, so the fractions are getting bigger. Everything's positive in that red area. So that's going to positive infinity, which means this whole quantity here is going to negative infinity. 1 minus infinity is negative infinity. And then if you multiply negative infinity by -1/2, we get positive infinity. So it diverges, which is what we would expect based on the power on x. Okay. Now, if we do an improper integral, let's suppose we do something like 1 over, let's do 1 over x to the 1/3, something like that, from 0 to 1. So here, we're expecting convergence because the power is now less than 1 and we're dealing with a vertical tail. And again, this is not a definite integral, even though it looks like a definite integral. So we want to make sure we do the limit as whatever letter we pick, it's going to go to 0 from the right. Integral, bless you. So we get this thing. We add 1 to the exponent, we divide by the new exponent, a to 1, factor out the 3/2. So we end up with 1 to the 2/3 minus a to the 2/3, as a goes to 0. So again, here it's really easy to assume that a is going to infinity just because we mostly do that. Don't make that mistake and say, oh, this is 1 minus infinity. So this is 1 minus 0. This is going to go to 0 as a goes to 0, so we end up with a finite value, so the improper integral converges. All right, so improper integration. Don't want to lose points on that.
Don't lose points on anything.
You don't want to lose points on anything. But these integrals for improper integrals, the integration part, they're all pretty easy. You know, most of the time it's just power rule. So you don't want to lose any points on power rule. Okay, integration by parts. So we've done a lot of integration by parts. Let's look at one example that is super easy to mess up. So let's suppose we want to integrate arctangent of x squared dx. Let's just do an indefinite integral. Okay, integral of, so arctan of x squared. We're going to use integration by parts. And there's no choice here, right? We only have one function there. Traditionally, we think of integration by parts as kind of a reverse product rule. And we're like, okay, let's let u be part of it and dv be the other part of it, and we have to figure out what goes where. If there's only one factor, it has to go with the u. Right? You can't put it with the dv because to get to v from dv you integrate and then you're back to where you started. Right? So it has to go with the u. So we're going to put it with the u. So it's our only choice is to do that. And that means that dv is just dx. Integrate, you get v is x. So here, differentiating. What is the derivative of that?
1 over x squared plus 2 or times 2x.
So that for sure, and then we have to do the chain rule. So we have to put a 2x in that numerator. Right? Chain rule, we have to differentiate the inside at the end. If you don't do that derivative right, you're going to be hosed. Because that's going to be important when you start doing the uv minus v, you know, all that stuff. So now integration by parts says u times v. So that's going to be x inverse tangent of x squared, uv, minus the integral of v du, the bottom row. And when we do the bottom row, we get an x times an x, right? So we get 2x squared over 1 plus x to the 4th dx.
get 1 plus x to the 4th?
The derivative of arctangent is 1 plus 1 over the inside squared.
Okay, good. So
1 plus 1 over the inside squared. So now we get that. And do we know how to integrate that?
I don't.
Do
I
I?
wanna think about it.
I mean, trig sub is the first thing I would think of. Yeah, making problems up out of thin air is a little
You
dangerous.
plug in for x squared, and then you get
Yeah, if we did I don't see any u sub that's gonna work.
u sub's not gonna work. But if you do, what is it? It's not something. Well, it's tangent, right?
Yeah, if we do a trig sub with tangent,
X squared to U squared.
if you did dv as x squared, split it up, no, you could do it that way.
dv, we can't split this up at all. This is just one thing.
Okay.
So that can't be broken apart. So on the test, I have to create something that's going to be easy to integrate here.
But what
So
happens if it was like tan inverse of x times x squared?
like an x squared on the outside?
Yeah. So
Yeah, that would be,
products.
yeah, if we had a product, then that could be possible, for
You know,
sure.
We probably could do another integration by parts.
Yeah, we could do this with another integration by parts.
Don't want.
That's possible. But the bottom line is that once we get through here, there's only one thing to choose for you. I will give you one where that's integrable, more obviously integrable. Let's do another one. Let's suppose we have something like integral of, oh yeah, we should do that one actually. We should do a twist.
Seeking cube.
Seeking cube would do it. So let's do this one. Yeah, so if we're doing integration by parts once, this just has to be easily integrable if we're just doing it once, which is what I would give you on the test if we're doing a regular integration by parts. If we're doing the twist, remember that we are going to need to call this integral something because we're going to invoke it later. And so here, when we pick our u and our dv, it doesn't matter. If we see that we have an exponential and a sine or an exponential and a cosine, where both of their derivative sequences just start repeating themselves, sine, cosine, e to the x, e to the x, doesn't matter which one you pick. So if you know that you're going to get that infinite loopy type of thing, we're going to do that. And the derivative here,
2e to the 2x.
2e to the 2x. Integral here,
Cosine. Sorry, negative cosine.
negative cosine. So then the original integral, which we call omega, is going to be uv, so minus cosine of, actually usually we put the e to the x in front, so that it doesn't look like it's part of the angle. So uv minus the integral of v du. So v du is going to be a negative, so that's going to make this positive. And we're going to get 2e to the 2x cosine x. Then we do it again, and here's where you have a couple of choices, and I think the best choice is to leave the 2 inside so that you're not having to factor. So I would let u equal this 2e to the 2x and dv be cosine. And we just have to make sure that we choose in the same pattern. If we let dv be the trig of originally, we have to stick with that pattern. And then what's our du going to be here?
4e to the 2x.
Yeah, 4e to the 2x dx, and b will be sine. So then our omega, all this stuff comes down out in front. And then u times v minus the integral of v du and that's where we're back again. So integral of e to the 2x sine, that is what we said omega is. And so our next step here, these two carry down, and this becomes minus 4 omega. So we have omega on the left, minus 4 omega on the right. And as soon as we add these omegas to the other side, we need to add a constant of integration.
Never forget Charles.
Don't forget Charles. Always throw Charles into the mix. Charles needs to be considered. So then we divide, so we get negative 1/5 e to the 2x cosine of x. We get all this. We get all this stuff. Plus c, plus Charles.
Or else you get all of your points taken away.
Yep. It's all or nothing.
Only on Thursday.
Only on Thursdays.
Yippee.
Okay, so integration by parts with a twist.
Could we do extra review on like the series?
Yeah, that's what we're going to do next. So geometric series first. Let's see, so that is a geometric series. Not necessarily in the right form. So we want to rewrite this. You should be seeing this numerator as 2 times 2 to the k. Your geometric series form is the arc form, a_r to the k. So we want the exponent on r to be just k. So we have to do whatever massaging necessary so that the exponent is just k. And then here, we're thinking of this as 5 to the negative 1 times 5 to the k. And this starts at 3. So we're almost there. We're almost in geometric form. So now the constants can be pulled out to the front. So that's 2 divided by 1/5, which is 10. And then we've got our series starting at 3. And if we write this in r to the k form, now it's in geometric series form.
And A is just 1.
A is what happens when you plug in 3 for head.
Yeah.
Wait, well, what happens if the 5 and negative 1's at the bottom? Does it come at 5?
Yeah, so it goes to the top, which is why it's
Yep. So 5 goes to the top. Dividing by 1/5 means multiplying by 5.
Okay.
So now the A is found by picking the initial index. So that's going to be 2/5 to the 3. So that's 2 to the 3 over 5 to the 3. What about the R value?
2/5.
2/5. So does this converge or diverge? So this converges because this is less than 1, therefore converge, right? So the next step, if it converges, we want to find what it converges to. You can do this next step for any series. S is equal to A over 1 minus R. Even if the series doesn't converge, you can plug this in and get a number. But it only makes sense if this converges. If that diverges, then you're done. You don't find S for a divergent series. There is no S. So our S here is going to be 10. We've got the 10 out in front. And then it's going to be A divided by 1 minus R. So A divided by 1 minus R, multiplied by 10. If we multiply everything by 125 to clear out this fraction in the top, then in the bottom we have 125 minus. If this is multiplied by 125, 25 times 2, which is 50. So we'll get that. So when all is said and done here, we're going to get 80 over 75. Divide out the 5. What's that, 15 and 16 or something? So that'll be the sum of the series. Make sense?
Clear as mud.
What type of series, is this a geometric
Geometric series.
series?
Geometric.
We go over, what is it, summation by power? You know which one I'm talking about?
P series? No.
P series, but
Which one?
subbing in into,
Oh, with the x's?
with like subbing, finding the.
Interval of
derivative
convergence?
And then subbing back into the power series.
So interval of convergence?
Yeah.
Yep.
That should just be 8/75, no?
Or, the 10 from before is.
So Watkins equals 1, is it diverge or converge?
If what's one?
If the R is 1,
That's
If
how it went.
R is 1, so if you come up here, if you have R is 1, it's not harmonic. If R is 1, you have 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, so it diverges.
P series.
If R is
R1
1.
is-
R is not less than 1.
For a P series,
For a-
R1 is harmonic.
less than-
For a geometric.
P
it's
series,
a summation of 1.
P series is different, yeah.
It's just a summation of A technically, right?
Yeah, summation of A, if R is.
Which is not helpful.
Okay, so, and we wanted to do power series. So, let's see, we want to do an interval of convergence. Interval of convergence. Let's take a look at
Number 12 on the last test.
number 12 on this test. Yeah, that's a good one.
Ever stuck in a problem, just go to 0.
Right, Bryce?
Yep, just so I can see the steps.
That is a good one.
It's so bad. It's not common.
Okay, so this. So first off, there's a couple of things I mentioned after the test that I want to reiterate here. So we are looking for a power series centered at 1. And the first common mistake is to say, oh, well, I noticed that g of x is just f of x squared, which is 100% true. That is true. But if you plug in x squared right there, then you don't have a power series. A power series must be in the form, a power series is always some constant multiplied by x minus the center, whatever we want to call the center, raised to a power. And that's the form of a power series. Just x, not x squared, x minus the center. So if you do this substitution, yeah, it's true, but that's not a power series. Is it a series? Yes. But it's not a power series. It's not a series of powers of x. It's some other, odd series. So that's not what we want to do. So we want to figure out, do we take a derivative or do we take an integral to get from f to g? And so if we rewrite f as x to the negative 2, shouldn't take us too long to realize that we want to take a derivative. We want the power in the bottom to increase. And so if we take a derivative here, we get negative 2x to the negative 3. Bring down the power, subtract 1. So now the power in the bottom is getting bigger, so we're on the right track. And then we do one more derivative. One more derivative, negative 2 times negative 3 is 6x to the negative 4. Bingo. Now we're where we want to be. Right, G is that thing down there. So this tells us that f double prime divided by 6 is equal to 1 over x to the 4th, which is G. So we now have a roadmap of how to get to g from f. Take f's second derivative, divide it by 6, and then we get to g. Okay, so that is our roadmap. So then we go to the power series for f, take 2 derivatives. So when we look at the power series for f, so f is equal to summation, starts at 0. This stuff here, these 2 terms, or factors I should call them, these are constants. That's constant. If you differentiate a constant times the power of x, the constant just comes down. Right? It doesn't matter if it's -1 to the k, -1 to the k plus 1. If it's a constant, it just comes down. So the first derivative here, all we do, this is a constant, it just comes down, staying out in front like it always does. Bring down the k, subtract 1 from the k. So the constant part floats, just keeps on coming down.
So then go down.
And then this is going to go up to 1 though, instead of starting at 0, because if it was 0, this would not be a polynomial anymore.
Yep.
X minus 1 to the -1 is not a polynomial. So we get to our second derivative,
Bring down the constants again.
bring down the constants again, that's going to bump up to 2. These constants are just floating on down. And we bring down 1 more. Subtract 1. There we go. Second derivative. Now we're golden. Now g of x is 1/6 that. So now we just put a 1/6 in front. That one starts at 2. And so here is the power series
Centered at 1.
centered at 1. So there is the power series for g. And then the last thing,
Yeah.
interval of convergence. When we take derivatives or integrals, the endpoints don't change. The only thing we have to do is test the endpoints, because maybe we get an alien vice grip and include it, or maybe we exclude an endpoint that we started with, or whatever. Now our intuition in this case, we've seen that derivatives tend to lose integration convergence at the ends. Integration tends to gain it. So we assume it's probably not going to be convergent at either endpoint. So 0 and 2. So now we test. So 0. And this part should be fast. There should be, you just have to plug it in correctly. We don't need the constant in front. That doesn't change any convergence stuff. And we have all of this mumbo jumbo. We're plugging in 0. That's going to give us a -1 to the k minus 2. We have one step here. You could even do it in your head if you wanted to, but when you combine these -1s, you get 2k minus 2. What is the parity of this exponent? Odd or even?
Always even.
Always even, right? That's always even. So that is just equal to 1. So that is all equal to 1. We don't even need it in there because it's equal to 1. So this is what we have. So does that converge or diverge?
No.
That diverges. That a sub k does not have a limit of 0.
Apple illusion.
Right? The limit, this is a sub k. And limit of a sub k is not 0, therefore diverge by divergence test. All right? Everyone agree that that limit's not 0? Those k's are in the numerator, and as k goes to infinity, goes to infinity. If we look at the second endpoint, if we look at x equals 2, it's going to look very similar. The only difference is that we're plugging in a 2 here. 2 minus 1 is 1. 1 to the k minus 2 is 1. Right? 1 to any power is 1. So when we do this, we end up with something super similar. What kind of series is that? Alternating. But the important piece for this alternating series is that this is a sub k. For an alternating series, a sub k is everything but the switch. Which is the same as down here. So we can say the limit of a sub k is not equal to 0, therefore diverge by divergence test. With the alternating series test, the step that I recommend doing first is this one. They put it in the book where you showed that it's decreasing. That's crazy. It's better to show that the limit is 0, because if the limit's not 0, why have gone through the trouble of showing that it's decreasing? And so the divergence test is built in as step 1 to the alternating series test. If the limit of a sub k is not 0, it diverges instantly.
It doesn't change.
So that means that the interval of convergence doesn't change. So we're going to keep it as 0 to 2.
And our radius is 1.
And the radius is 1. Radius is 1.
Cool.
Okay, how about, should we do a binomial series one?
Yeah, well, what do you think?
I think we should do a binomial series is
What's
so,
under review stuff? What have we not covered on the review?
binomial series is super important.
And it's on the review, let's do it.
Let's just all agree to fail
Is
that.
binomial?
13.
Yes, it is.
Yeah, let's do binomial series.
Can we just all agree to fail that problem, you know?
So let's suppose we have something like this. That can be written as an infinite series. We have a binomial, 2 terms, raised to a power. If your binomial isn't in this form, you would have to manipulate it to make it 1 plus something. And that's how you would break it apart. It's not going to be that complicated, but you could.
And it always needs to be 1 plus something.
Yes,
Similar to trig sub.
just like trig sub. And so this is going to be -4, choose 0, plus -4, choose 1 times x. So your first step, it should feel very geometric. So these are the first 4 non-zero terms. This is a series, so it should have dots. These are not fractions, so you should not have a fraction bar. Not a fraction. And the interval of convergence will be given to you. So when x is negative, I forget off the top of my head whether I think we exclude both endpoints. Does someone have it there close by? So this was chapter 11. So we can't figure out, yeah, so it's going to be, we're going to exclude both endpoints when we go to a binomial series. So we're in this category here, less than -1, so exclude both endpoints.
And that will be told to us.
And that will be told. That shall be revealed. So this interval is -1 to 1, like that. Okay, so our series then, -4 choose 0, 1, -4 choose 1, -4. So that part is instant. And it's a power series, starts with a constant. Don't start with an x, start with a constant, and then the x. And now we have 2 of these that we've got to figure out. So -4 choose 2, we're going to start with -4. We're going to subtract 1 and get -5. So this is going to be 20 divided by 2 which is 10. So that's what this term is going to be. So plus 10x squared. And then we do negative 4 choose 3. So that's going to be negative 4 multiplied by negative 5 multiplied by negative 6 over 3 factorial, which is 6. So this will be negative 20.
20. Oh,
It's the same thing as before, times negative 6 divided by 3.
Divided by 1 extra factorial piece.
1 extra term at the bottom, 1 extra term at the top,
1 extra factor.
1 extra factor.
So there it is.
and then if you just wanted us to find the air, we'd just plug a jug.
So if we want to find what?
Like which term has the air?
Oh,
less
yes.
than-
But this is not an alternating series. Well, I guess it's eventually an alternating series. You're right.
Yeah,
Yes.
it is an
Yes, we could do that. We could do that. We could do that. So if the question said how many terms do we have to add together to have error less than 0.000001, yes, we could do that. The problem with that is that I've got to give you something really close because there's no general pattern. Like with those ones that we typically use that alternating series method for, you can say, oh, a sub k has to be less than 0.00001. And you can set your a sub k less than that. Here we don't have a generic a sub k formula. Right? This is what the a sub k's look like, but we don't have a generic formula. So it would have to be a term really close to the front.
Like you could say, analyze like what, 1/10, and then the third term is less than 1,000.
Yeah, so it'd have to be really close to the front.
Even lower than a 10, so that's like 100.
Okay, so so the interval of convergence here is -1 to 1. So now a typical question would be, what about 1 minus 3x to the -4? What's the power series for that? First 4 non-zero terms. We're going to replace all these x's with -3x. So if we replace that x with -3x, up here we're going to end up with 1 plus 12x. And then the -3x goes into the x squared, so we're going to get 9x squared.
90x squared?
Say again?
90x squared with a 10.
And then a 10. 90x squared. Everyone okay with that? So all the x's are turning into -3x. Here the negative is going to bounce that negative, make it a positive. 3x cubed, so we're going to get 27. So we're going to get like 540 x to the 3 plus, etc. Then we have to modify our interval of convergence. So we replace the x with -3x. So we also do that with the interval of convergence. And so the interval of convergence is going to be -1/3 to 1/3, excluding endpoints. And we don't have to test endpoints. When you do a substitution into the IOC, you get what you get. You don't have to retest endpoints. You only retest endpoints if you're differentiating or integrating.
So that's one problem. First we do that, then series account.
Yeah, that's one problem.
Okay.
So it would
Yep.
be find the power series for 1 plus x to the -4 and use it to find 1 minus 3x to the -4.
Right. Yep.
What's the difference between like problem and question?
Semantics.
Semantics. I like that answer. Semantics.
What's semantics?
Words.
Oh,
They're just different words.
Yeah, you could think of.
Synonyms?
Yeah.
Synonyms are words that have the same meaning?
Like technically you could have, I don't know, a question for the problem, but in this case.
Okay, so let's see. Binomial. Let's do one more interval of convergence type thing. Let's suppose we have a series that looks like, let's think for a second here. So k, x to the k over,
Completely out.
now let's not put a k in the top.
Getting too used to it.
Let's see. K returns. Let's do something like that. Okay, so there is a power series, x to the k over k to the k. We want to know what the interval of convergence is. So we know it converges for its center. Its center is 0. Every power series converges at its center. Has to. We want to know, is there anything else for which it converges? So, ratio or root, what do you want to use?
The root test.
The root test actually works very well here. So we can take the limit of the kth root of a sub k, and here notation is super important. We are taking the absolute value of anything with an x on it. Okay, absolute value, because x could be negative. If x is negative and k is odd, you'd be trying to take, well, I guess if k is odd, you could take the kth root of an, never mind. You want to have absolute values on there. So when we take the kth root here, we get absolute x over k. The kth root of x to the k is absolute x. The kth root of k to the k is k. All right. We know that for the geometric series, the root test and the ratio test, less than 1 gives us convergence. So we want to know, what are the x's that make that true? So that's what we're thinking about. That's where we're going. And what is this limit? 0. Because the absolute value of x has nothing to do with k. K is in the bottom, so these fractions go to 0. And then we compare it to 1. And I heard somebody say that this is true always, right? 0 is always less than 1. So therefore, our interval of convergence is all reals. And what would we say the radius of convergence is? Infinity. Half of 2 infinity. That make sense? So this is a super easy one, but you've got to be careful. There's notation with the absolute value, and it's very tempting when you get this limit of 0, it's very tempting to say, oh, the radius of convergence is 0. No. When we get the limit value, we compare the limit to 1, and we ask ourselves, what are the x's for which this is true? And it's true for every x. Doesn't matter what x you plug in there, that limit's going to be 0. So your interval of convergence is all reals.
Is it possible to have an interval of convergence of exactly 2 terms or 3 terms?
It's either 1 term or an infinite number of terms. There is no in between.
Because
Because it's either a point or an interval.
an interval has infinite.
And an interval has got unlimited terms. All right?
What if it has 2 centers?
Eric?
Although with the power series.
We take the square root out of the limit?
Or sorry, the absolute value.
Oh, yes. So you can do this intermediate step here where you can, if the limit is sort of tricky to evaluate, maybe you would do this next.
But that's just where it's
So it's, we know the limit's going to be 0. Yeah, so this is going to end up being absolute x times 0, which is 0. Yeah.
Oh, yeah.
So because the x has no k in it, you can always factor it to the front of that limit and then evaluate it.
I don't like being able to
Anyways,
like
want to feel
each other
younger?
until Monday.
I want to feel younger.
And I just think that your age I just think of the age you want to be.
Okay, I'm thinking.
Yeah, there's the same amount of instantaneous
It
points
didn't
of
work.
time. There's the same amount of instantaneous points of time as your age is not.
Alright. Hey, Mr.
True,
Rollins, I
true.
can convert Cartesian to polar, but I can't convert polar to Cartesian. Is it right if I convert it to Catholicism instead?
It's your choice. May you burn.
I'm saying that you're,
No, I'm not.
Yeah, what's
I might go.
Oh, I probably have it hanging out, lingering,
So I can use it,
so you can put it on your fridge.
so I can use it to study. Thank you.
Yeah. Happy birthday.
Thank you. I'm old.
You old. Now you officially old.
Now I'm officially old.
Yep.
how
I'll
old
see
are
you
you?
As
Thursday.
soon as you hit 40.
How old are you?
40.
40?
Yeah, I get extra credit because my house got flooded and I couldn't study.
What?
My house got flooded on Saturday, so I was fixing it like 2 days and we're still fixing it.
Oh
So I
no.
couldn't study 2 days.
Oh no.
Then I get at least 1 point.
Yeah, 1 point.
Okay, thank you so much. Or it's again.
Were you able to fix it all?
No,
Do you have like
we're still fixing it.
carpet?
Yeah, because like drain system wasn't connected,
Uh-huh.
so it's like flooded everywhere.
Drywall also?
Dry, also dry, but it's just like a carpet.
Nightmare.
That is.
We had a huge flood in 2013 and our whole basement flooded. Carpet, drywall, we had to cut off the bottom 3 feet of the drywall. And, oh, no fun. And this was just Saturday?
Yeah.
During all that rain? What town are you in?
Huh?
What town?
Oh, Westminster.
Westminster. And why did it flood? Was it because of the...
Because, and it's flooded in the first place, we don't know why, but
It's never flooded before.
no. Like.
Did water come in the windows or under the
No,
foundation?
because there's like, the most flooded places where there's no windows,
Yeah.
and like the walls are dry, but the guy who fixing it right now said like, it may be like the dirt.
Under the foundation?
Yeah, but my neighbor, had also the same problem, and like, neighbor across, so we're thinking it's maybe a pipe burst.
Oh.
So he called it Westminster Water.
Well, that would be good if it was the city, because then it
Yeah, it's gonna be
cover
insurance.
insurance. But so it wasn't coming out. That's interesting.
Yeah.
I hope it's not. Hopefully you can get insurance because it's such a
But
pain.
didn't he, that means he was old enough to drink alcohol when I was born.
Yeah. So was I.
Or no, but the thing is, at the time I was born though.
The moment,
At the same
the
time.
instantaneous moment,
Like he
like your mom was doing when you were
Or
born.
no, the person who just turned 40.
Turned 40 last week. Yeah.
So I mean, this is not exactly the same. I was to say, it's pretty similar. The time that he was allowed to drink alcohol, officially not allowed to drink alcohol,
Yeah, he's almost even.
it was about the same
Yeah.
amount of time I was born.
It depends on where he was born too.
First in the United States.
Different countries, because some
Inside
countries
the
have a
United
different
States.
drinking age.